Okay, in this video, we're going to do a linear regression. And the only difference here between what we did with the least squares method is that now we have a non-time variable for our independent variable. So we still have our same formulas. And instead of having x be time, we're going to have it be something other than time. And so the key here is going to be really arranging our data. So every time we have 2 here, we're going to have to move that 2 back and line it up with another y value. So we could have 6 here. All right. So in other words, what that graph would look like is we have 1, 2, 3. Okay. And then y we have 1, 2, 3, 4, 5, 6. So let's put our data in red. So for this here, 1, 1, that would be this point here. 2, 4, 2, and then 4. 3, 5 would be here. And then 2, 6. 2 would be back here. And that point would be here. Okay, so it's a very, very simple example of how we've got to arrange our data. And we can get Excel to do this for us if we want to. But mentally, we always got to keep straight what we're doing. And so this is not time. This is some other variable. We could say this is the amount in billions that people get paid in a certain area. And this is the amount of sales that we do in that area. And we want to see what the relationship is between the amount that people get paid and the amount of things that they buy. So that's what that would do. Otherwise, the method is really the same. So let's go to Excel and do an example. Okay, so in this particular example, we want to figure out the relationship between what I just mentioned, payroll and sales. So let's just say salary. And sales. Total salary. And this is going to be our independent variable. This is going to be our dependent variable. We want to see how much sales depends on total salary within an area. And so we have some data points. We know that one time we captured total salary as 1 billion and sales for that time period were 2. Okay, so the main point here this is probably the most important point of this section technique, is that these are not time periods, but we probably want to get our data in order so that we can just look at it the right way. So for example, we have 2 out here, we have 1 down here, and 1 up here. So we could do this manually. We could do this. So this is probably much better. So here we can see, just want to verify that everything moved the way we wanted it to. We have 2 points of 1. That's not too surprising. So we can kind of see here, again, we still want to see that we have a trend of some sort before we start using a method. And we can see here that we have somewhat of an upward trend. As salary increases, so does sales. And that's really what this is telling us. If you remember your statistics days, we could compute R, the correlation coefficient, which tells us the strength of the relationship between these two, to what degree they're correlated. I'm not going to have you do that, but that's another formula, and we could do that here in Excel. The main thing to see is that we have an upward trend. As salary increases, so does sales within a particular area. So we can get rid of this. Let's suppose we want to see 10 and 11. If salary was 10 billion and 11 billion, cumulative, what would our sales projection look like? So from here, our method is the same. Just to run through it, hit list, sum of x, y, n, average x, average y, sum x squared. Okay, create my XY column. I don't want all these blue, so black. Okay, that goes there. Again, don't get tricked. How many marriages, XY data points do I have? 1, 2, 3, 4, 5, 6 this time. So N will be 6. Don't take these into account. My average of X is going to be my sum of X divided by 6. And so that's going to be 3. And then same for Y. Y is going to be a lot closer to X this time. It turns out it's less. And then finally, I'm going to go ahead and create an X squared column. Get that sum. And get that over here. Okay. Moving right along. Get my b numerator, my b denominator, b. And a. B numerator again, sum of x times y minus my n times my average x times my average y. My denominator is my sum minus n times my average x squared. Numerator divided by denominator. 0.25. So we can see the slope is much less than in our previous example. That really is neither here nor there. It's just something to note. Okay, A, again, is our average y, using our formula up at the top here, minus our slope, times the average x, 1.75. So our regression line, y, is equal to the intercept, 1.75. To give ourselves a little space here. Plus that slope, 0.25 times x. So if we want to predict for 10, I'm just going to go back here, grab that y-intercept, grab our b, and multiply by our salary, our independent variable of 10 billion. 4.25, drag that down. And so this says that if total salary is 10, let's just do this here, kind of focus on apples to apples. Okay, so if our total salary is 10, our predicted sales will be 4.25. 11, 4.5. Now here's another neat thing about this method is not only do we have to go into the future, we can also kind of go inside of these variables in the future. So what do I mean? Well, we have data for, we have a couple points on $1 billion of salary. We have some on 2 and 3, and then we have an outlier of, not an outlier, but we have a point out there of 7. Well, what about 5 and 6? So we could do 5 and 6 down here as well. We don't have to go beyond 7, and it would be the same method. So if we were interested in, well, what if salary went to 6, knowing that 7 might not be indicative of the future, maybe 6 is more realistic, so we could use 6 and then predict future sales at 3.25. So that's really it on the linear regression. The big takeaway is that a lot of what we learned on the least squares method, we can transfer to this method. The formulas are the same. The thought process is the same. We need to detect a trend as independent values increase, that dependent values have some sort of trend related to that. It could be an increase or it could be a decrease, but either way, it's one of the two. The formulas are the same. The process is the same. We're going to determine B, then A, and use those to determine our regression line, and use our regression line to predict the values we want to predict. A couple differences. One is that our X values are not time periods. They are non-time periods. So in this case, it's salary. It could be demand as a independent variable and something else as a dependent variable. Or it could be demand, in this case, sales, as the dependent variable and something else as the independent variable. Occupations, that would be a little bit more difficult to do, so we'd have to translate that into numerical values. We might not want to do that. It might not be the best example. But the point is that these X values are not time periods. And then finally, another big takeaway is that we can predict inside of our, because it's not a time period, we don't necessarily have to go out in the future. We can go inside of the variables that we have. And I suppose we could do that with the least squares method as well, if we wanted to. So that's linear regression. And with this video and the other video, that's our class for this week.